Hello and welcome back to our GPU optimization of Advanced Encryption Standard course. So in the first three lectures, we have seen the theoretical part. We have seen what the block cipher is, how Advanced Encryption Standard works, and how we can use the mode of operation with the block cipher. Now that we have the theoretical information, it is time to implement our algorithm. So generally, I first start with type definitions because different compilers have different types, and sometimes writing long code like unsigned long int, etc. We can simply shorten them like U8, U16, U32 like this, or sometimes I simply refer to them as bit 8, bit 32. So in the implementation of AES, actually we will be using U32 almost all the time, rarely U8, but we won't be needing the other two. And here's an example. For instance, AES has some round constants that we use during the key schedule algorithm. So we simply use XOR byte values. But generally, the value that we are going to XOR is on the leftmost byte of the 32 bits. So instead of storing these round constants as a byte, we can store them as 32-bit values like this. So let's start with the key schedule. So recall that this was the top boxes are the master secret key, 128-bit. So we refer to them as 4 columns from starting from left to right. We can refer to them as RK0, RK1, RK2, and RK3. So our master key is actually as an input to our key schedule function. We put the master key here. So our initial round keys, RK0, RK1, RK2, and RK3 comes from this master key. So here we write these equalities and use them. So the function works like this. As the input, it takes the master key and provides round keys, as many as you want, because as I mentioned, depending on the key length, we have different number of rounds, and so different number of round keys. But for the AES 128, we will have 10 rounds. So we will have 10 round keys together with the main master key, which can be seen as the 0th round key. So we initialize them to these values. Then we update this key as in the figure, as in the following code. So the code does the following. For instance, we take the rightmost column, make it equal to some temporary value, then apply rotate it and apply sbox operation on it. Then there is a round constant XOR here. So this rotation, sbox, and round constant addition actually happens in this part of the code. Then we simply XOR this value with RK0 to obtain RK1, etc., etc. So these XORs are performed here, as you can see. Okay. And in a for loop, this way we update it. So from the master key, we obtain the first round key, we write it back here, obtain the second round key, and so on and so forth. So this is the host part here means that we are doing it on the CPU. Actually, if you need to perform the key schedule only once, there is no point of doing it on the GPU side. Simply do the key schedule operation like this function, then send the round keys to GPU, and storing them in the shared memory allows us the fast access. Okay. So recall that we had the advanced encryption standard like this. So this was just one round. So we had the input here and have the operations adding the round key, which is a simple an XOR, then perform 16 sbox operations for each byte, then rotate the rows, then perform matrix multiplication on columns. So in our implementation, one approach might be, storing this 16 bytes as, unsigned characters as 8 bits. But generally, this causes a performance loss. So generally, what we do is we store these columns as 32-bit values and perform the operations on these columns, since we are going to have matrix multiplication at the end anyway on columns. Okay. So let's look at the sbox operation. Recall that it was simply a table lookup. So we gave the example like this. If the input is 3B, you find the third row bit column and write the result. So this is just a table lookup operation. So you can simply store these values in an array like this, right? And you can, for the input, you can get the output. So this is the basic implementation of an S-box. Then recall that we had a rotation of rows. So the 0th row does not rotate it. The first row is rotated simply 1 byte. This one is rotated 2 bytes, and this one is rotated 3 bytes, etc. So this is simply a rotation operation. If you are keeping your input as bytes, you are simply swapping the places of bytes. If you are keeping rows as 32-bit values, it's a simply shift operation and an OR operation to obtain this rotation. So it's simple. But then next we have this matrix multiplication. Recall that this was how it works. So this is the MDS matrix for AES. And these values are multiplied with these values. But recall that this was done in Galois field. So when I actually multiply 2 with x0, so I see the x0 as a 7-degree polynomial, then multiply with 2. But this time the polynomial size might increase. So I need to do a polynomial reduction to obtain the real value. And same applies for when I multiply with 3. But when I multiply with 1, the value doesn't change, so there's no reduction operation. So the problem comes from multiplying with 2 and 3. So you can either implement Galois field operations, do the polynomial multiplication, then do the polynomial reduction. But the thing is, for instance, if I multiply 2 with the value x0, x0 is just a byte. So it can take 256 values. So I can simply pre-calculate multiplication by 2 of every byte value, also multiplication with 3 of every byte value, and keep it in a table like shown here. So this is multiplied by 2. So for instance, if you multiply 0 with 2, you get 0, but if it is 1, you get 2, etc. But once the values increase, we also do the polynomial reduction and obtain the results like this. So instead of doing the Galois field operations, you can simply turn this multiplication into a table lookup. So similarly, you can do the same thing for multiplication by 3. So you end up with another table. So this is just array values in a C or CUDA implementation. So these are the main operations that we need. And as you can see with these simplifications, you can simply implement AES, but don't forget that in the last round, we don't have the mixed column operation. So for AES 128, we can write the code for a single round in a for loop of 9 rounds, and then perform the last round. So in the last round, we again have add round key, S-box operation, shift rows, but not mixed column. So instead here we simply do a final round of key XOR. Okay, so that is basically the whole thing. So in the next lecture, since that we have a basic reference C implementation, we will turn it into a CUDA, and actually CUDA codes are very similar to C codes. Then we will turn this into a table-based implementation, because the current approach where we implement everything as in the picture can be referred to as reference implementation or naive implementation, but we will see there is another method called a table-based implementation, which will speed up the process on GPUs significantly. But when we do this table-based implementation, we will keep some tables in the shared memory, and we will observe shared memory bank conflicts, and we will also see a method to just remove these shared memory bank conflicts to obtain the record-breaking performance. So thank you for listening.